Good.
Thank you. Okay, hi everyone. I'm very sorry that I cannot make this trip. I want to thank organizers inviting me and offer me this opportunity to give this Skype talk. Okay, now let's begin the talk. So the talk is on cyclic Higgs bundle. This is joint work with Song Dai from Tianjin University. Okay, let's do some setup. Again, let S be a closed oriented surface of genus G greater or equal to 2, and then pi1 be the fundamental group. And we consider Riemann surface structure sigma, and then denote K as the canonical line bundle of this Riemann surface. Okay. We consider non-abelian Hodge theory. Non-abelian Hodge theory relates several modular space. First, we start with the Betti modular space. It's all the conjugate classes of semi-simple representations from fundamental group to G as a Lie group. So next modular space is the Durham modular space. It's a gauge equivalent class of semi-simple flat G connections. So implicitly it's on a principal G bundle. If we add a choice of Riemann surface structure on this surface, we can consider an intermediate object, which is the deformation space of equivariant harmonic maps from the universal cover of the Riemann surface into the symmetric space associated to this Lie group G, which is the G quotient is maximal compact subgroup. And lastly is a Dobel modular space. Also, we call it a modular space of Higgs bundles. So the element is a polystable G Higgs bundle, and we will give a precise definition later. So this modular space are homeomorphic to each other. This is the core of non-abelian Hodge theory. So we can see they're related as a homeomorphic. So Betti modular space is a topological object, and Durham modular space is a differential object. And the harmonic map space is a Riemannian geometry object, and Dobel is a complex geometry object. Okay. So the most importantly is the second and third homeomorphism. That's the non-abelian Hodge. It's relating the Durham and the Dobel through looking for harmonic maps. Okay. So now we finally define what a Higgs bundle means. A SLNC Higgs bundle over the Riemann surface is a pair E-phi, where E is a rank n holomorphic vector bundle with a trivial determinant. So it's that corresponding to the S. And then phi is a holomorphic bundle map from bundle E to E tensor with the canonical line bundle of the Riemann surface. It satisfies trace equal to 0. If we want to consider G Higgs bundle, we can add corresponding conditions. And the theorem by Hitching and Simpson is that if E-phi is a stable SLNC Higgs bundle, then there exists a unique metric H on this bundle, solving the Hitching equation, which contains two parts. First part is the curvature of chain connection, and second part is the Higgs field and its Hermitian joints, Lie bracket. So we want to say their sum is equal to 0. And then this solution is called the harmonic metric. So because of this theorem, we actually obtain from a stable Higgs bundle a flight SLNC connection, which is the sum of the chain connection plus Higgs field and its Hermitian joint. So in fact, the flatness of this connection is equivalent that our solution H satisfying the previous equation. So consider the holonomy of this flat connection. We obtain a representation from the fundamental group of the surface into SLNC. And then use the information as this Hermitian metric and this flat connection. We parallel transport the Hermitian metric to one fiber. Then we actually get this row equivariant harmonic map F from universal cover of Riemann surface into the symmetric space associated to SLNC. So which is actually this SLNC quotient SUN actually is the space of all Hermitian metrics over Cn of determinant 1. So conversely, by the work of Donaldson and Collette, given a semi-simple representation rho from fundamental group into SLNC, there exists a rho equivariant harmonic map to the symmetric space. So the main philosophy to keep in mind is that this non-abelian Hodge correspondence is not explicit because it's by solving a highly non-trivial PDE. For example, if we have a lateral action on one side, it's hard to see how this action acts on the other side, even though we know it's homeomorphic. These two modular spaces are homeomorphic. So for example, we can consider the Teichmuller space. So the definition is all isotopic classes of complex structure or hyperbolic structures. Okay. We can also view it from Higgs bundle. If we fix a base Riemann surface structure sigma 0, any point in Teichmuller space, here we consider as a hyperbolic matrix as points in Teichmuller space. So this G is a hyperbolic metric. So any point corresponds to a SO2R Higgs bundle over this base Riemann surface sigma 0, where the bundle is case 1/2, direct sum case minus 1/2. This case 1/2 is a choice of square root of the canonical line bundle K. And the Higgs field is just by taking case 1/2 to case minus 1/2 tensor to K, which is 1, and the Q2 as the upper triangular part. Okay. So it's very explicit. The bundle is fixed and the Higgs field is only parameterized by this quadratic differential Q2, which is holomorphic. Okay. But in fact, we also understand what this Q2 by from the harmonic map. So this Q2 is also the Hopf differential of the harmonic diffeomorphism F from sigma 0 to this Riemann surface SG. Oh, I didn't write the isotopic to identity. Okay. So Hopf differential is the 2-0 part of the pullback metric. So this is a relationship between looking at the Higgs bundle, we actually see explicitly the information of the related harmonic map. So this Hopf differential measures the nonconformity of the harmonic map. So in particular, if this Hopf differential vanish, the harmonic diffeomorphism is conformal. That means the point sigma we consider is actually the base Riemann surface sigma 0. So in this case, the existence of solution to the Hitching equation is actually another proof of the uniformization theorem for Riemann surface, just looking for hyperbolic metric in its conformal class. So this case is called a base friction case. So now we go back to the modular space of Higgs bundle. There are two important objects on the modular space of Higgs bundle. So one is the Hitching fibration and the Hitching section. And secondly is the C star action. And we'll also introduce a family of Higgs bundles, which is the cyclic Higgs bundle as in the title. Our main goal is understanding this C star action and find out the special feature of the Hitching section for cyclic Higgs bundles in the space of harmonic maps. So it's kind of understanding one direction of the non-abelian Hodge. So from Higgs bundle to the space of harmonic maps. So if we have something happened in this modular space of Higgs bundle, we want to say the corresponding thing in the space of harmonic maps. So the Hitching fibration is a map from modular space of Higgs bundles to the direct sum of holomorphic differentials. So it's very similar to the Chen-Weil theory. We are given a Higgs bundle Phi. We just take the trace of phi square, trace of phi cube, and then until trace of phi to the n. In this way, we get a holomorphic quadratic differential, cubic differential until n differential. And the Hitching section is going backwards. So if we are given a tuple of differentials, Q2 to Qn, we can construct explicit Higgs bundle out of the data. So the bundle E is fixed. It's again just as the Teichmuller case. Teichmuller space case is from the canonical 9 bundles information. So it's of rank n, and the power is decreasing by 1. And the Higgs field is written explicitly by this given data, and it's always in this form. And the important thing is that all such Phi has a holonomy inside the real part, which is SLNR, instead of just in SLNC. So we can see in the case n equal to 2, the image of Hitching section is actually the Higgs bundle description of Teichmuller space. And then the representations arising from Hitching section form a connected component of all the representations into PSLNR, and it's called the Hitching component. So it's a lateral generalization of Teichmuller space, and they indeed share lots of similar properties. And we have a base and friction point, which is the image of origin under this Hitching section. So we don't see any differential there. It's just the bundle is still the same bundle, and the Higgs field, we only see this lower off-diagonal 1, 1, 1 there. So the corresponding representation is the composition of the base friction representation composing with the unique irreducible representation SL2R to SLNR. And the picture for Hitching vibration and Hitching section are as follows. So this at least can give you the feeling that Hitching section really intersect each Hitching fiber once. Of course, it's a section, but we actually want to say why it is special. And second, we come to this C-star action. So a key attribute of Higgs bundle is that it has a very lateral C-star action. So it's defined by just T times E phi to E T phi. So just times the Higgs field by this T. So of course we need to check whether it's well defined, since it's not really one Higgs bundle, it's a gauge equivalent class, but it's well defined. And related thing is a Morse function defined on the modular space of a Higgs bundle is by taking the trace of phi star. Here phi star is the Hermitian joint of phi by the Hermitian metric H. So then we take the integration of it. And the relation between this C-star action and the Morse function is that the fixed points of C-star action are critical points of this Morse function, F. So this is very important because it's useful to determine the topology of a modular space of a Higgs bundle using the Morse theory. And especially useful in lower rank case. And because of the non-abelian Hodge, we can see this C-star action also acts on the space of representations. But it acts in an explicit way. Okay. So now we introduce cyclic Higgs bundles. The cyclic Higgs bundles are always in the form as so the bundle E is direct sum of 9 bundles. So L1, L2 to Ln. And the Higgs field is also very special. It takes L1 to L2 twisted by K, and take L2 to L3 twisted by K, and it goes back by this gamma n. So take Ln to L1 twisted by K. So it actually forms a loop. Okay. But we have a condition here. We want this gamma j non-zero if j is less than n. So we don't require gamma n to be non-zero. So it can be a loop, or the last arrow can be cut. So because now we have explicit form of this Higgs field, we can really see the Hopf differential. In case n greater or equal to 3, the Hopf differential will just vanish because it's a trace of phi square. If you just calculate, you can see it's vanished. So if we consider Higgs bundle of cyclic Higgs bundle of rank greater or equal to 3, the harmonic map is minimum. And we can see cyclic Higgs bundle also intersect Hitching section. And in each Hitching fiber, so we can see cyclic Higgs bundle in Hitching section are always in this form because we already require both conditions. So it's actually parameterized by the n differential, the highest differential. So let's recall our main goal is for cyclic Higgs bundle, we need to understand the C-star action and then try to find what's special of a Hitching section. So the first goal is talking about the monotonicity of pullback metric along this C-star flow. So the motivation is along C-star flow of the modular space of a Higgs bundle, we want to understand how the associated harmonic map So if n is greater or equal to 3, it's also minimum, vary through solving Hitching equation. So the remaining metric on the symmetric space is induced by the Qiongling form on this Lie algebra SLNC. So if the harmonic map is conformal, the pullback metric of the harmonic map is given by the trace of phi star times 2n. So our first theorem is that if Phi is a cyclic Higgs bundle with the next arrow non-zero, then announce the C star orbit as the absolute value of T increases, the pullback metric GT of its corresponding branch minimal immersion strictly increases away from branch points. So here the condition gamma n being non-zero is important. If it's 0, it's fixed under this C star orbit. So we don't need to say the change because it doesn't change. Okay. And what means branch point? The branch points are exactly the point that phi equal to 0. So if phi equal to 0 at one point, under this C star is to stay at 0. So it's always branched at the same point. So we cannot say at those points change. But away from such points, the pullback metric strictly increases. If we integrate the metric over the surface, we have the corollary that announce this C star orbit as the T's norm increases, the Morse function strictly increases. So if you remember, the Morse function is actually the integration of the metric for the conformal case. So I want to remark that the monotonicity for Morse function is not new. So this corollary is not a new result. In fact, Hitching showed that with respect to the Kähler metric on the model space of Higgs bundles, the gradient flow of the Morse function is exactly this R star part of C star action. So this is using global geometry to know that this Morse function strictly increases as T's norm increases. So what we just did is we improved the result for cyclic Higgs bundles from this integral monotonicity to pointwise monotonicity. And we expect this to be true in general, that the pullback metric always strictly increases. If it's conformal, I need to say if it's in the case being conformal. Our second goal is to say some special thing about cyclic Higgs bundle in Hitching section. So again, recall the cyclic Higgs bundle in Hitching section are only parameterized by the holomorphic n differential. And the motivation is we want to investigate that as an immersed submanifold, how the image sits inside the symmetric space by looking at its extrinsic curvature. So the second theorem is if Phi is a cyclic Higgs bundle in Hitching section, and F is the associated equivariant harmonic map into the symmetric space. And then let sigma be the tangent plane, any tangent plane of the image of F. If we calculate the curvature, sectional curvature of this plane inside the symmetric space X, it satisfies this formula. So it's strictly less than 0 and greater or equal to a number there. So for this symmetric space, which is SONC quotient SUN, it has a sectional curvature as from -1/n to 0. So we can compare our bounds K sigma in the theorem with this global bound for the whole symmetric space X. We can say that we obtain a non-trivial upper and lower bound on the extrinsic curvature K sigma. And the upper bound here means that this minimal immersion is never tangential to any flight in the symmetric space. And moreover, it is sharp in the asymptotic sense. That means if we consider the Higgs bundle going to infinity, which means, for example, we consider the ray parameterized, the cyclic Higgs bundle parameterized by TQN, where the T goes to infinity. So as the T goes to infinity away from a discrete set, or this curvature will go to 0. So that's what we mean it is sharp in asymptotic sense. So let's compare the base and fiction case, which is really the image of the origin under Hitching section. In this case, the sectional curvature is -6/n squared times n squared minus 1. So we can compare this one with the lower bound in the theorem. However, in case n greater than 3, this curvature for the base and fiction case cannot serve as a lower bound for the curvature, for this extrinsic curvature here. So this is because we show that at the zeros of Qn, the sectional curvature K sigma is strictly less than this fiction case. So you can check all these numbers are the same, or this formula -6/n squared times n squared minus 1 are the same. So this is kind of surprising, because when we look at the formula, on the right-hand side, 0 is our limit. It is actually the case where Higgs bundle going to the limit. So we kind of hope that the lower bound is the base and fiction case. However, actually that's not true. It's not always between the base fiction case and the limit case. It actually goes lower. So for general Higgs bundles, one should not expect there is such a non-trivial lower bound at immersed points. For example, in the case of cyclic Higgs bundles with the gamma 1, gamma 2, gamma n in the Higgs field, if there are exactly n-1 terms of gamma I have a common 0 point, then the curvature of the tangent plane sigma at that point achieves the most negative, which means K sigma equal to minus 1 over n. So this says we cannot expect a non-trivial curvature bound for general Higgs bundles. But if it's inside the Hitching section, we can expect a non-trivial curvature bound. So the next thing is a comparison inside the real Hitching fiber. So we know that if we calculate the Hitching fibration for cyclic Higgs bundle by taking trace of phi square, trace of phi cube, until trace of phi n, we can see it's always nice in the Hitching fiber at 0, 0, 0 until the last one with the Qn there. And it's n times Qn because we use the trace of phi to the n. So it's also the Qn is also the determinant of this Higgs field. So again, inside each Hitching fiber at this 0, 0 n Qn, there is a special point, which is the cyclic Higgs bundle in the Hitching component, parameterized by Qn. So we want to compare inside the same Hitching fiber, what the relationship between this special point, the cyclic Higgs bundle inside the Hitching section, and the other cyclic Higgs bundles in that Hitching fiber. So our theorem is let E tilde, B tilde be a cyclic Higgs bundle in the Hitching component, parameterized by Qn. And E phi be a different cyclic SLNR Higgs bundle. So it has some extra symmetry, such that they have the same determinant, which means they are in the same Hitching fiber. So in the case n equal to 2, 3, 4, the pullback metric of the corresponding harmonic maps satisfy this strict inequality. So that means, in some sense, the Hitching section dominates other points. We said for the cyclic points. So in the case n equal to 2, this is shown by Leroy and Tonazan. And we expect this to be true in general case. So it's really saying if we consider E tilde, phi tilde as a Higgs bundle in Hitching component, and E phi as a different SLNR Higgs bundle in the, so this is not SLNR, we want to expect for everything. So it's a distinct SLNC Higgs bundle in the same Hitching fiber. Then the pullback metric satisfy that the Hitching component dominates all the others in the same Hitching fiber. So of course, as a result, we can say the Morse function also satisfies this inequality. So it sounds very strong because even for the Morse function level, this result is unknown. I think I asked many people in doing Higgs bundles. I think that they kind of believe so, but there are no such theorem yet. But then we ask for this pullback metric, so it feels very ambitious. However, in the SL2C case, this is already shown by Duron and Tonodon in the same paper I mentioned in previous page. So we think this conjecture is really can be true. So we can say some applications to maximal SP4R representations. So let's first say what maximal SP4R representation mean. So for every reductive representation rho into a non-compact Hermitian Lie group G, we can define the Toledo invariant tau rho. So it satisfies the Milnor-Wood inequality. So the normal that bounded by the rank of this Lie group times the genus minus 1. So the representation rho with the maximal Toledo number is called maximal. So in the case for SP4R, Gaussian showed that there are 3 times 2 to the 2g plus 2g minus 4 connected components of maximal representations. So inside of all these components, there are 2 to the 2g isomorphic components of Hitching representations. So basically, these 2 to the 2g coming from the choice of canonical line bundle square root. And other than the Hitching components, there are other 2g minus 3 exceptional components called the Gaussian components. So they look very similar and have good properties as this Hitching component. So combined with the work of Labourie and Brian Collier, for every maximal SP4R representation rho in the Hitching component and the Gaussian component, there exists a unique rho equivalent minimal surface of this universal cover of S into this metric space for SP4R, which is SP4R quotient U2. So we can then state the monotonicity property and the curvature bound for the equivalent minimal surface for maximal SP4R representation in the Hitching component and the Gaussian component. So as corollaries of previous theorems. So this is because for all such representations, there always exists a Riemann surface such that the associated Higgs bundles are cyclic. So in this is actually because it's lower rank. In this lower rank case, cyclic Higgs bundles actually can achieve all such maximal representations. So as the corollary of the comparison inside the real Hitching fiber section, we can compare these two kinds of maximal representations. So we can state in this way is for every maximal representation SP4R representation rho, okay. SP4R representation rho in the Gaussian components, there exists a Hitching representation J such that the pullback metric of this J equivalent minimal surface strictly dominates the one for rho. So this is really saying for every rho in the Gaussian component, there is a J dominates it in this minimal surface viewpoint. So the main tool we use in proofs is the following maximal principle per system used to analyze the harmonic metric solving Hitching equation. So let's have assumptions. So sigma G is a closed Riemannian manifold. For each I, let Ui be a C2 function on the manifold minus an isolated subset, Pi, this Pi. It can be empty. Okay. Suppose Ui approach to plus infinity around Pi. So this is very important. It cannot go to minus infinity because we want the right sign. Okay. So let P be the union of all this set Pi. So suppose Ui satisfy such an equation system. So it's a Laplacian of Ui. This Laplacian is with respect to the Riemannian metric G there. Okay. So plus summations of Ui's using the coefficient Cij. So equal to Fi. So here Cij are continuous and bounded functions on this surface, on this sigma minus the set P. Suppose Cij satisfy conditions. So the first one is if it's not on the diagonal part, or the off-diagonal entries have to be non-negative. And it also satisfies column diagonally dominant, which means if you sum over each column, it's always non-positive. And lastly is fully coupled. That means the equation system cannot be decomposed into two different systems. Okay, so it's fully coupled. So here, why we introduce this subset Pi? So because we actually need to deal with the functions times this gamma I. Remember gamma I from the Higgs field? So it might have zeros. So that's the Pi. The zero, they are the zero set of gamma I's. So for Ui satisfy this system, we have a precise statement for the maximal principle. Is that suppose the previous assumptions hold, and now we add a condition for this Fi. If Fi is non-positive, then under each of these following conditions, we have Ui greater than 0. So this is the system style of maximal principle. Because if we have one function, you can see in this way, like if the equation is less or equal to 0, we get we get U greater than 0. So now we want this one equation maximal principle to be generalized to be true for system. We actually need to give conditions on the coefficient, because the maximal principle in the end, it needs the right sign. So the condition for Cij is satisfying these ABC conditions. So what's really new is about this condition B, the column diagonal dominant, because if you check the literature, usually it's about the row diagonal dominant, and this really gives different feature. So basically, the condition here condition 1, 2, 3, they are just to prevent some trivial thing to happen. For example, the first one is we don't want all this fi to be 0. Or condition 2 is we don't want there are no bad points. Okay, and the condition 3 is also very new for this maximal principle for system. There are always no a priori conditions on the solution thing. But actually for the monotonicity, condition 3 really helps. Okay. So we have under condition 1 or 2, we get ui greater than 0. And condition 3 can imply either every ui greater than 0 or ui are constant 0 function. So this lemma is our main tool because this is how we deal with the system of this heating equation. So the monotonicity and the comparison inside the heating fiber, these two parts of result can be proved by deriving the right equation system to apply this maximal principle by checking which condition to be satisfied. So here I want to remark that the equation system is not already there. We have to check what kind of unknown functions need to be right, and how to make it into coefficients and times unknowns, because almost everything is unknowns. But we have to sometimes put one part as coefficients, one part to be unknowns. So that's what I mean, deriving the right equation system. However, for the curvature part, it's not just by applying the maximal principle. It needs much more work. Okay. And thank you.
Okay, so are there some questions?
Hello, Qiongling.
Hello.
So if you look at your first theorem, can you scroll to your first theorem?
Yes.
So my question is, so you say that as you have this dominating, I mean, can you say how the pullback metric grows with t, with the absolute value of t? Asymptotically.
We can say asymptotically.
You can say, so what is there? Is it grows exponentially or?
It's like you know that it in the end what this g looks like. It looks like a t square.
It looks like t square. Okay.
Times the
original.
times the q and norm square.
Okay. And that's this also away from the branch points?
Yes.
Same. Okay. Okay. And then for your second theorem.
Okay. Yes.
So the lower bound you have on the curvature, right? I mean, you like you said, right? If you make t go to infinity, the curvature should converge to 0 almost everywhere, right? The section.
Yeah, that's the thing.
Right,
that's the thing. You don't have everywhere. There are some
some points that you're missing.
Yes.
But can you improve? If you allow your lower bound to depend on t, on the absolute value of t, right? Can you improve this lower bound when t gets really big?
No, so let me show this one. So you see the last remark. The last remark says that at the zeros of this Qn, the sectional curvature is always less than this number. So that's a uniform thing. Do you see it?
Oh,
because
I see.
No matter what t, that point's curvature is always has this bound, upper bound. It can never go to 0. That's also, yeah.
Okay, thanks.
Hi, Qiongling.
Hi,
So in your
hi.
next, it's a third theorem.
Third,
Yeah, so you're looking at Hitching fiber, right? Or
yes.
yeah, so is there some kind of asymptotics here as well that you can talk about? Just like in the previous one, you were scaling t, and you had some idea of what the asymptotics are. Is there a similar kind of thing here, or what's the picture?
Yeah, I think this is very interesting that we actually almost know that asymptotically they are equal. Almost all the how to say, as long as go to infinity, it's actually just using the information in the base, in the Hitching base. So we should expect, and I think it's almost proved by this limit of Higgs bundle, like by Mochizuki, by knowing the asymptotic solution for Hitching equation for general SLNC Higgs bundle. So we can expect that in the limit they are equal. Everything in the Hitching fiber are going to be asymptotically equal. However, the dominance property is actually independent of this asymptotically equal, because even though you know it goes to be almost the same, you cannot see which one is bigger. Right? Yeah.
Okay, well, in that case, let's thank the speaker again for a very nice talk.